Welcome back to Why This Universe. Before we get started today, we have a pretty exciting announcement. Why This Universe is officially joining the University of Chicago Podcast Network. This is an exciting new network bringing you different shows where you can just learn so much about everything from economics to politics to literature and now physics included. For example, if you've been enjoying Why This Universe, you should definitely check out Big Brains. Big Brains brings you the engaging stories behind the pioneering research reshaping our world. Change how you see the world and keep up with the latest academic thinking with Big Brains, part of the University of Chicago Podcast Network. So a lot of our previous episodes of Why This Universe have dealt with these big open problems in physics, like dark matter or axions or, interpretations of quantum mechanics or something like that we don't really know that well. But today we're going to be talking about something that we actually understand super well, so well that some people, right, Dan, some people call this the most successful theory in physics.
Yeah, it's debatable exactly which the number one most successful theory in physics or science is, but this is definitely a contender, if not the number one slot.
Right, and so we're talking about the standard model of particle physics, right? The heart and core of everything we know about the fundamental particles and how they interact.
That's right. So from a branding perspective, this is a pretty lousy name. If you wanted to make something seem exciting and kind of spectacular, you might not name it the standard model, but that's what we call it. That's the name we're stuck with. But as you said, this is like an incredibly successful theory. It makes, thousands of different precise predictions that we test in experiments and just keep getting the right answer. The standard model is this incredible theory that just won't be proven wrong, at least not yet.
But, that being said, it doesn't explain everything. This seemingly perfect theory, it can't be perfect. So today we're going to talk about what the standard model is and then also its shortcomings, right?
Yeah, its limitations, what it does and doesn't do. It does the stuff it does really well, but there's certainly a lot of things that we would like a theory one day to do for us that the standard model cannot.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
So if you were to ask, what is the smallest, most indivisible stuff in the universe, the standard model would tell you the answer. So as a whole, the standard model describes 3 out of the 4 known fundamental forces. So there's the electromagnetic force, everything to do with electric charges and magnetism, and there's the weak force, everything related to how particles decay. And then there's the strong force, the one that keeps protons and neutrons held together in a nucleus. And the standard model does this all through describing a set of elementary particles that you could never divide into smaller pieces. There are ones we call quarks and others we call leptons, and then there's a third type called bosons. So things like protons and neutrons are made up of quarks. Leptons include things like electrons and neutrinos, and the bosons include the particles that mediate the fundamental forces. We'll get into that more later.
The force of gravity, the standard model doesn't touch that. We just don't know how to build a quantum theory or a particle physics theory that does gravity. All the efforts we've made to do this so far have either failed or been inconclusive. So at this point, we just set gravity to the side and say someday we'll find a particle physics theory to do that, but we don't have it yet.
So we know that the standard model explains these 3 forces, and it explains all of the elementary particles that we've ever detected. But before we get into how exactly it does this, let's talk a little about the history.
So let's go back to the early 20th century. At this point, physicists really only knew about 3 kinds of elementary particles. So we knew about electrons, we knew about protons, we knew about photons. And that was it. But then in the 1930s, we started to discover new kinds of matter. We discovered the neutron in 1932 and the positron also in 1932. A few years later, in 1936, the muons were discovered. And then in the 1940s, pions and kaons were discovered, neutrinos in 1956, so on and so forth. The list just kept getting bigger and bigger and bigger. And at this point, these just seemed like a arbitrary list of new things that were being discovered. There didn't seem to be any obvious organizing principle behind them. No one was predicting what we were going to discover next. Not really, anyway. We were just discovering things and trying to fit them, into some sort of theory, but not doing a very good job of it. One of the responses to this was when the muon was discovered, the Nobel laureate Isaac Rabi said, "Who ordered that?" Like, he was just totally astonished. Like, this doesn't fit into anything. We don't seem to need it. I don't know why this exists in nature, but there it is. And they wanted some explanation, but none was forthcoming at that point.
Maybe you could make an analogy with chemistry, with something like the elements in the periodic table, right? Maybe before we had this overarching structure that we could put them in, and like now we know that the different elements are organized by how many electrons and neutrons and protons they have, etc. But like before that, they were just discovering elements here and there.
Exactly, yeah. So when you discovered 20 different elements and measured their properties, but didn't know why they were, in the pattern they were in, this is very analogous to particle physics in the 1950s or something. And when it was figured out that all those chemical elements were just different combinations of protons, neutrons, and electrons, it all kind of fit together in a neat, organized framework that was very predictive and powerful. That's what the Standard Model would ultimately become.
And if you Google image Standard Model, you can see kind of the analogous periodic table of elements, but now table of particles.
Yeah. The main difference, as I see it, is whereas the elements in the periodic table are made up of smaller things, protons, neutrons, and electrons in different combinations, as far as we know, and we have good reasons to think it's true, all of the particles described by the Standard Model are indivisible. They're the smallest pieces of matter and energy that can exist. So I think we should pause for a second and ask kind of what might seem like a simple question, but it's actually pretty profound. But what's it mean for us to know that a particle or a particle species exists? When I normally talk about something existing in the universe, I mean like you can go to some place in the universe and find it. So there's a record store half a block from my house. That record store exists. It's here. When a physicist says, for example, muons exist, it is true that there are muons in our universe right now, but what it really means is that the universe's laws are written in such a way that it's possible for energy to take the form of a muon. It's like one of the options that energy can be packaged in. Even if there were no muons in the universe right now, the laws of physics tell us what we have to do to make one. They're one of the ways that energy can be manifest in nature. And it turns out there's a finite list of ways that energy can appear in nature. And each of those is what we call a particle species or a particle type or a particle. So it turns out that when you try to build a theory that describes a group of particles and their interaction, not just any combination of those particles can be present in a mathematically self-consistent theory. In some theories that you might want to have written down, you might say, here are the 6 particles that exist and here's the way they interact or something. In some of those theories, if you tried to calculate certain physical properties like masses of particles or how strongly they interact with each other or something like this, you would find that the answer to those questions would be infinity. So those are like broken theories. Those are theories that don't make any sense. So particle physicists feel they have to limit themselves to a subset of all the theories they can write down, the ones that don't have these infinities kind of built into them. In particular, we talk about theories that are renormalizable, which means you can get rid of the infinities that might emerge. Those are the sorts of theories we have to limit our investigations to.
Right. And I guess to be clear, it's not that those theories predict these infinite masses and we're like, no, that can't happen. We're just like, no, that kind of result means that theory just isn't valid in that calculation.
That's right. The theory itself doesn't describe a self-consistent picture of reality.
So, for a long time, all of the infinities that were showing up in physicist calculations seemed really problematic, and the future of particle physics hinged on finding a way around them.
So in the 1970s, while he was still a grad student, this Dutch theoretical physicist named Gerard 't Hooft showed that all theories that have this particular kind of property that we call gauge invariance were automatically mathematically self-consistent in the way we're talking about. So we're not going to really get into what gauge invariance is, but it turns out that if a given particle physics theory has this thing built into it, this kind of symmetry, then it will automatically avoid all these problems with infinities that other theories might have. So for example, if you took like a simplified version of our electromagnetic theory and just had like electrons, positrons, and photons interacting with each other in this theory, it turns out that that simple theory would be self-consistent in the way we're talking about if and only if the photon had exactly zero mass. It had to be entirely massless. So if the photon has no mass, then this simple theory is mathematically consistent and all holds together. But if it had even the tiniest little bit of mass, it would be a disaster. It would be a theory that doesn't make any sense. So we know the photon has to be exactly massless. And even just experimentally or observationally, we know that the photon has, if any mass at all, a vanishingly small mass. Its upper limit is like 10 to the minus 27 electron volts, which is just wildly, wildly smaller than the smallest masses we've observed among any other particles.
Oh, and also just to clarify there, we're not saying that the photon has that small mass. It
No.
could have zero mass. It's just that's our upper limit that our experiments have gotten to. It has at maximum that tiny mass, yeah.
I think it is exceedingly likely the photon has exactly zero mass, but experimentally it's hard to measure zero. What you do is show it has to be smaller than some number. And in this case, it's a really, really, really small number. In the 1960s, Murray Gell-Mann and others worked out that there were a bunch of the different kinds of particles we had discovered in nature, like things like protons and neutrons and others, that weren't really elementary particles. They were made up of smaller particles, things we call quarks and gluons. Protons and neutrons are each made up of three quarks held together by these gluons, and other sort of particles are actually bound up quarks and antiquarks together in pairs. So the theory that Gell-Mann worked out showed that to have this kind of mathematical consistency we're talking about, the gluons that held together these particles had to be exactly massless, a lot like the photon. And the symmetry of this theory describes the strong nuclear force in the same way that the symmetry that described the electromagnetic theory described that force. So we begin to see this kind of overarching pattern emerge about the way that these forces are manifest in nature.
Right, so this pattern involves some kind of symmetry that's describing how this force is acting on different particles.
Symmetry is at the heart of the Standard Model, yes, for sure. So each of these symmetries comes along with a particle, or sometimes more than one particle, that communicates the force in question. We call these things gauge bosons. So the photon is the gauge boson that's associated with the electromagnetic force. And the gluons, it turns out there are 8 of them, these 8 gluons are the gauge bosons that communicate the strong nuclear force. If these particles didn't exist, those forces wouldn't exist. The reason why charged particles interact with each other is because photons are being passed back and forth through space, communicating the electromagnetic force. And the strong force between quarks is because gluons are traveling back and forth through space, communicating the strong nuclear force.
Yeah, this might be weird if you've only ever heard of the electromagnetic force as the thing that makes charges repel or attract, or like magnets repel or attract or something. It's actually just an exchange of photons causing that interaction.
Yeah, and if I take my hand and I try to push it through the wall, I mean, most of my hand and most of that wall are empty space. The only reason my hand stops is because the photons in those charged particles are passed back and forth, creating the thing that we call the electromagnetic force.
Right. I like to think about textures like that. It's actually just the electromagnetic force creating little different patterns.
It's a good thing we have photons. So the weak force turns out to be a little more tricky than the strong force and the electromagnetic force are. For one thing, it was known very early on that the weak force is a really short range. It only extends through space like 10 to the minus 18 meters, which is, an awfully small distance. And from a particle physics perspective, this means that whatever the particles are that communicate this force through space, they have to be really heavy. It turns out they're about 100 times heavier than a proton. If we were to write down a theory like this that includes very heavy or very massive gauge bosons to communicate the weak force, this turns out to be one of those theories that isn't mathematically consistent. So this seemed like a big problem for trying to understand the weak force back in the 60s. But Peter Higgs and others in the 60s worked out a solution to this, but it involved this thing called the Higgs boson. So they predicted that there would be this new particle called the Higgs boson. Well, Peter Higgs didn't call it that, but it got to be known as the Higgs boson as years went on. And that particle interacts with the particles that communicate the weak force, what we call the W and Z bosons, in a way to make them become heavy. So like deep down, these particles are massless, just like the photon and gluons are, but they act like they're heavy. We even say they're heavy in our normal way of describing it because of the way they interact with the Higgs boson. So the W and Z bosons that communicate the weak force weren't discovered in an experiment directly until the 1980s. And the Higgs took even longer. It wasn't until 2012 that we saw the first definitive evidence for that at the Large Hadron Collider. Although I work at Fermilab, so I'm like almost legally compelled to brag that Fermilab saw some pretty compelling hints of it earlier than that at its own accelerator called the Tevatron. But all the same, the LHC deserves a lot of credit. They did discover the Higgs in 2012, even though we had some glimpses of it first.
Yeah, I think how old was I in 20? I was 14. So that was, I think, the first big physics discovery that I was really alive for.
You're making me feel really old right now, Shalma.
I'm sorry, I'm just young.
Yeah, that was like yesterday for me. All right, so putting this all together, we have this theory with three different symmetries that correspond to the three different forces we're talking about: the electromagnetic force, the strong force, and the weak force. And those forces act on 12 particles that we call leptons and quarks, 6 leptons, 6 quarks. And by the late 1960s, all of this had kind of come together. Physicists like Sheldon Glashow, Steve Weinberg, and Abdus Salam had kind of worked out the mathematics of this, combining it with the work from Murray Gell-Mann and others. In fact, they used to call this thing the Glashow-Weinberg-Salam theory, but now we just call it the standard model of particle physics. These 6 quarks and 6 leptons also come in a particular kind of patterns, these groups, 3 different groups that we call generations. So the first generation of these particles include the electron, one of the neutrinos, and 2 quarks. Quarks we call up and down quarks. And then there's like 2 copies of that group of 4 particles. There's a second generation with a particle a lot like the electron that we call a muon, which is 200 times heavier, another neutrino, and 2 heavier quarks. And then there's a third generation of even heavier particles. Today, the heaviest known particle is the top quark. This was discovered in the 1990s at Fermilab. To put in context, it's about 340,000 times heavier than an electron.
It's pretty weird that there are these different generations of almost identical particles, except just with different masses. We don't really know exactly why that happens.
If you were just speculating about how a universe and its laws might be structured, I don't think you would have guessed this. There's really no super compelling explanation for why these particles come in 3 generations and not 2 or 6 or something. But 3 seems to be the number, best we can tell. So Shalma, do you want the good news first or the bad news first?
About the Standard Model?
About the Standard Model.
Let's take good news first.
All right. So the Standard Model has been ruthlessly tested by physicists for decades. For, 50, 60 years, all of the particle accelerators and the other experiments that have been trying to scrutinize the Standard Model, they've been trying to break it, trying to show where it fails, trying to go beyond it. They've all, been unable to do that. It just keeps passing every test we throw at it. So this is super impressive. Along with general relativity, the Standard Model is the most experimentally successful theory of all time. Also, it's worth appreciating that the Standard Model made predictions of things that hadn't been observed at all at the time. So like the W and the Z and the Higgs boson and other particles like that were predicted to exist according to the Standard Model before any physicist ever saw any evidence of them. This just came from the mathematical structure of the theory and what had to be there in order for it to all make sense.
Right. So super predictive, super successful.
That's right. And then there's the bad news. So in a lot of ways, the Standard Model, at least to me and to a lot of people, seems pretty complex and has a lot of ad hoc features. It's kind of like a Rube Goldberg machine of physics. Physicists, generally speaking, like theories that are mathematically elegant and simple. Maybe they're based on some sort of first principles that a bunch of different stuff derives from. Theories that are like this tend to be more predictive and require less input for more output, whereas the properties of the Standard Model in many cases are just things we have to go out and measure. There's nothing about the structure of the Standard Model that tells us how heavy a bunch of different particles need to be or how they should interact in certain ways. And we just have to kind of go out into the laboratory and find out what those things are. An ideal theory wouldn't have that feature. So let's compare the Standard Model to a theory like Einstein's general relativity. So you can derive general relativity, or at least one can, from a couple of like foundational principles. So you say, like, for example, the laws of physics are going to be the same in all frames of reference. And you take those things and you just work out the logical consequences and you get general relativity. And you could take those equations that Einstein wrote down in 1915 and 1916, and those are exactly the same equations that general relativists or experts in gravity are using today. They haven't changed because they really can't. It's like the only way those principles could be manifest in nature. And if you want to, use those equations to calculate what gravitational waves should look like, or black holes, or the early universe, or whatever, Einstein's original equations still do that job. That's kind of opposite to the Standard Model. The Standard Model was built as we measured one more thing and had to add a new feature. And then we measured something else and added a new feature. And then it turns out we need a second and a third generation, so we add those. And, the list goes on and on. There are a bunch of, ways in which nature could have been different. And we've just kind of found out how it is and measured it and wrote it down in this complicated way. In particular, the Standard Model has 19 separate free parameters. So there are 10 different particle masses that we can't predict, but we just have to go out and measure. So those could have been any numbers as far as we know, and we just measure them in the lab and find out what they are. The three forces could have had any strengths, and we just go out and measure them. And then there are other parameters, too, that describe how different quarks interact through the weak force and things like this. There's a quantity that we talked about in the Axion episode of this podcast that's one of the 19 parameters of the Standard Model. All these things, and we have no idea why these quantities take on the values that they do. Ideally, most physicists would like to have a theory in their drawer that would allow them to not just measure these values, but to predict them, to explain why the electron has a particular mass and why it interacts with a particular strength of force. But that's not the Standard Model. The Standard Model can't do that for us. In addition to all of these ways that the Standard Model leaves us wanting more theoretically, there are also just a number of things it doesn't try to address at all. There's no explanation in the Standard Model for how neutrinos get mass. We used to think neutrinos were probably massless, but we now know they have very small masses. And there's nothing but the Standard Model that allows those particles to have masses. So there have to be some new particles that exist that we don't know about that aren't contained in the Standard Model that allow for that to happen. Also, we know that there's a lot of dark matter in the universe. Nothing in the Standard Model could make up any substantial part of that dark matter. So something else, something beyond the Standard Model accounts for that. We know that there's much more matter in our universe than antimatter, and that somehow came into effect in the early universe. Nothing in the Standard Model allows for that to happen at the rate that would have to. So something new has to come in to do that. We also know that our universe expanded very rapidly in an inflationary period after the Big Bang. Nothing in the Standard Model explains that. And probably most importantly, the force of gravity is entirely left out of the Standard Model. We don't know how to include gravity in a theory like this, what we call a theory of quantum gravity. There are a lot of ideas, including string theory and loop quantum gravity, to try to do this, but I would say at this point, it's still an entirely open question how that's going to work out. A lot of physicists think that one day the Standard Model will be fit into some bigger theory, maybe a grand unified theory, or even a theory of everything, which would include gravity. But at this point, I think it's just an entirely open question. For now, it is a spectacularly successful theory, but one that we know, won't last forever. Eventually, or so we hope, physicists will discover the next bigger thing and replace their most spectacularly successful theory to date with something that can explain all the things it can explain and a lot of things it can't.
Right. I guess in a way, all the bad news about the Standard Model is actually good news for physicists because it means more work to be done. Our jobs are not obsolete yet.
If we ever reach a point where we can answer all of the questions that we're asking, I don't even know what to say about that. I just won't.
Just retire and be happy with it. Don't think too hard. So lots of physicists are still thinking about the Standard Model today. There are still people performing higher and higher precision experiments to make sure that the Standard Model stays accurate. And lots of people are focusing on what we call beyond the Standard Model physics. So trying to come up with new theories and ideas and trying to find new particles that can hopefully bring us closer to answering all those questions left open by the Standard Model.
Absolutely. So on the experimental side, we're using a Large Hadron Collider to measure characteristics of the Standard Model with even greater precision than we've done before. Right now, there's an experiment at Fermilab trying to measure the magnetic moment of the muon. That is one way that we can test the boundaries of the Standard Model with even greater depth. Maybe one day we'll build a new particle accelerator that's designed to do this sort of precision work, maybe one involving electrons instead of protons like they use a Large Hadron Collider. And then on the theory side, every single day on the preprint archive, there are dozens of new ideas for what physics might extend the Standard Model. So far, we have very little evidence for any of it, but someday that will change.
So thank you for listening. I hope you enjoyed today's episode. And if you want to engage with us more, we have a Twitter account. You can search @WhyThisUniverse and feel free to tweet at us with your comments, reactions, suggestions, what you want to hear next. We appreciate all kinds of feedback. Why This Universe is brought to you by the University of Chicago Podcast Network. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.